Hello. I think both are working.
Which one do you prefer, sir?
Both sometimes. If
Yeah,
one
just
switch off
switch off
something,
one.
you can switch off that.
Just long press this for off. Single press for on.
Off. Now it is on.
Yes, sir.
We can switch off that press. Yeah.
Need anything?
What are you doing? Yeah. So good morning all. Welcome to the first session of this Atal FDP. I will be delivering the session on AI ML applications in manufacturing, particularly in advanced finishing methods. I will show you some research progress, what we are working on and what our publications are on, and what is the AI ML application in manufacturing and all. So I belongs to NIT Warangal campus. Yeah. Artificial intelligence. So how we define artificial intelligence? So artificial intelligence is a science of making machines think, learn, and to act like human. It focuses on creating systems that can pre-receive their environment via sensors, data, and cameras, reason and make decisions, learn from experience, act to achieve goals. In a simplest way to define it, it's a science which makes the machines to learn, understand, and act accordingly. What is machine learning? Just I'm not going in detail about AI, ML, and all, but in applications, we'll discuss more on the research perspective. What is ML? Basic definition. ML is a subset of AI that enables machines to learn automatically from data without explicit programming. Instead of hard coding rules, we need data and the system find patterns to make predictions or decisions. Machine learning, many of the faculty might be working. So we have supervised learning, unsupervised learning, reinforced learning. So supervised learning, the algorithm learns using labeled data. So like the goal is learn the relationship between input and output. I think we are working on supervised learning during our problem statements. So you can see that the raw data input is collected and there will be supervised learning based, and we use the machine learning algorithms, processing, and then output printing. So what is the difference in supervised and unsupervised is, here we have a one particular item is not there, that is supervised. So there is no particular component which supervises the data. So it is unsupervised. So instead of that, we have interpretation and unknown output with no training data or no supervision is required. We commonly called as unsupervised learning. Many of them might be studied all this. So reinforced learning. Reinforcement is the another type where you can see the raw data as input, and you can see the components like environment and the agent and then the output printing. So model learns by trial and error method in reinforcement through reward and penalties. Goal is take actions that maximize reward over time. And we have a subset called deep learning. Deep learning is a subset of machine learning that uses artificial neural networks. So we also used ANN for our data. So I will be explaining that with many layers to automatically learn complex patterns from large amount of data. So we can see the difference between the machine learning and the deep learning. So most of the computer science faculties, they will be using the deep learning concepts, CNN and ANN, etc. So you can slightly observe the difference, like feature extraction in machine learning and feature extraction plus classification together in deep learning applications. Understanding AI, ML, and deep learning in a like the basic understanding. So artificial intelligence uses computer science and data to enable problem solving in machines. So machine learning refers to the study of computer systems that learn and adapt automatically from experience without being explicitly programmed. Deep learning is a machine learning technique that layers algorithms and computing units or neurons into artificial neural network that mimic the human brain. Okay, so just a small basic about what is ML, what is AI, and what is the other subsets. So we can look into this. And coming to in general understanding, so we are human. The boy or a girl born in Karnataka, so he trains to learn Karnataka language, right? He's trained to see the Karnataka films, Kannada films, and all. And then whenever you give some image or whenever you ask the question, so the boy is used to answer it because he's trained in the language and he's trained in watching, he's trained in several aspects. Okay, but I'm from Andhra, but I cannot speak Kannada. I understand Telugu, English, and Hindi, etc. because I'm trained in that particular languages. But we have that uh, intelligence. We have that intelligence to learn, to observe, right? And to understand, and then to execute. So the training is important here. Okay. So the training is called like how this kind of training we give to the machines, how this knowledge is shared to the machines. Another simple example, like earlier we used to go to means now also, like whenever we get any disease we go to doctor, right? So we go to doctor and then a radiologist, and we get some x-rays or CT scan, etc. And then we meet doctor, and doctor used to see the CT scan or x-ray, and then he used to identify the disease based on the result, right? And then suggest your disease, type of disease, and other things, etc. But nowadays, like the machines are trained in such a way, like it will give automatically based on its intelligence, based on the image, based on the result, it will automatically give some result and again further certified by the doctor. So what is the advantage means, if thousands of x-rays are there, if thousands of reports are there, thousands of people are having the same kind of problem, doctors are in hundreds or singles, okay, or maybe in hundreds, they cannot provide the input information to each and every patient personally, and they cannot generate the report for thousands or lakhs of report for a CT scan or X-ray or MR, whatever, right? So they are taking help of machines. Okay, the humans are taking help of machines. So this will minimize the errors as well as improves. And this technology will improve works more effectively when the proper intelligence is given to the machines. Nowadays, we all know how ChatGPT overtaked many other softwares and how we are using the ChatGPT box, etc. Right? For writing an email, for writing some report, whatever the information you require, nowadays we are going to ChatGPT and then giving the inputs and getting the output. Means these algorithms, the program behind are trained with the suitable knowledge is given to that particular apps, right? So you can take another example like, yeah, whenever you browse some data, right, in YouTube, if you are browsing some particular item, some particular data, automatically when you reopen it, automatically the related videos or related content will appear on your uh, uh, means your desktop, that webmaster or okay. So means some programs like Netflix, etc., it will recommend you automatically based on your taste. So okay, some background they are working on this artificial intelligence and machine learning algorithms, etc. So machine learning model, like how we collect the data, clean the data, pre-process the data, explore data, train data, tune parameters, test model, evaluate performance. So this is a subset, like this is the entire machine learning model, like how we perform the actions from 1 to 10, you can see. And these kind of actions, I will tell you when we have taken some case study and how the collection data is happen and clean data, explore data, how it is done step by step, we will see. Let us go to the case study and then we'll correlate this ML and AI and some algorithms like fuzzy logic, ANN, and we have used some optimization algorithms like Jaya algorithm, etc. So we'll see. So coming to case study, I work on in the field of advanced finishing methods. I hope all are manufacturing background. So we all know what is advanced finishing, right? So we know the importance of precision finishing, right? Advanced finishing. There are traditional methods and non-traditional methods in finishing area. Traditional methods like grinding, honing, and lapping. So we have some constraint with the workpiece. Like workpiece, we can grind only flat workpieces and cylindrical external surfaces, and it is limited to some simple geometry. Okay, whereas the RA value, the average roughness value range also will not meet our requirements. Coming to some advanced finishing methods like abrasive flow machining, magnetic abrasive finishing, magnetic float polishing, etc. So these processes will have more advantage in finishing complex geometries. We'll discuss one case study, and then we'll see the data, and then how that AI ML applications, etc. And also we'll see the application. So why high precision is essential? So to improve product performance, okay, to have a better compatibility with advanced technologies, efficiency and cost effectiveness. So precision is required when you are working on aerospace components. Precision finish and accuracy is required. Precision finish and accuracy is required in medical industries. So when you are working on finishing of medical implants, and as well as it is required whenever the parts are having friction between the assembly parts. And nowadays, we all know additive manufacturing and additive manufacturing components, how demand it is in the present era. So we are printing the complex geometries directly using several additive manufacturing techniques. However, these processes will suffer with some post-processing requirements. So these components after 3D printing, it requires some post processing, and that for post processing actually there are different methods, and one of the method is abrasive flow machining. Yeah. So outline of the today's presentation, like we'll discuss the background of the abrasive flow machining, which is developed at NIT Warangal, and the experimentation and the machine, about the machine details, and then we applied fuzzy logic, Zaya algorithm, ANN, etc. Like after collecting the data, real-time data. So we'll look into this case study. Yeah. So what is abrasive flow machining? So abrasive flow machining is one of the advanced finishing method which is used to finish the complex geometries. The principle of abrasive flow machining is pumping an abrasive laden medium through or over the component to be finished. Okay, so the medium is pushed by means of two hydraulic cylinders vertically. Medium flows from one cylinder through the tooling into the other cylinder. So there are two hydraulic cylinders, and then in between there is a tooling. So in this tooling we keep the workpiece, the complex geometry, and then we pump from one cylinder to another cylinder, that semi-solid media, passing through the target surface. You can see this is the cylindrical workpiece, and the target is actually to finish this cylindrical geometry. So the abrasive media is mixed with abrasive particles with a polymer gel. So the polymer gel is mixed with abrasive particles. When you are applying pressure to and fro, so the polymer gel will carry this abrasive particles to the target surface. I will show you a small video. Yeah, this is what I'm talking about. So this blue color is the workpiece, and this yellow is the medium. So we are pumping to and fro. So you can see that abrasives are targeting the surface. So some complex non-cylindrical holes, its internal finishing and external finishing. And this is the semi-solid media. It is a mixture of abrasive particles mixed with polymer gel. It looks like this. The polymer gel mixed with abrasive. So different grades of abrasives can be used. Yeah. So this is the flexible tool. This is a flexible tool we are using. So we are applying hydraulic pressure in the flexible tool, and the flexible tool or the media is coming out from the workpiece. So this is the workpiece here, the manifolds which are used in automobiles. So while traveling, it is finishing, deburring and radius. You can see here, the media is coming out from some complex geometries, micro holes, micro drills, and the media property is reliable in nature. We are pumping to and fro. So while traveling, actually it is polishing. It is polishing, radiusing, and deburring. You can see the workpiece, the complex geometry. So some complex geometries and it's finishing. So several automobile components. So non-cylindrical holes, non-circular. So these manifolds can be finished and deburred using this semi-solid medium. So we have different applications like in finishing of 3D printing components, aerospace industries, like wherever high precision is required. So we have applications. See, you cannot finish with simple processes like grinding, honing, lapping, etc. because of the complexity of the workpiece. So aluminum extrusion dies and it's finishing. You can see the channels and it's finishing. So even non-metals also we can finish. Bent pipes can be finished because of the flexibility of the abrasive medium. Metallurgical molds, etc. Yeah, I think you got some idea about the process. So we are pumping the semi-solid media to and fro, passing through the target surface. See, this is the workpiece here, and this is the tool. So while pumping, actually it is doing its job, like cleaning the internal surface, deburring it, okay, radiusing it, and you can have a controlled finishing using the sensors, right? So we are using some acoustic sensors to predict the surface roughness without measuring. Yeah. So the mechanism of material removal in this particular process is simple. The material is removed because of the abrasion. So we apply pressure, uh, hydraulic pressure, and then the abrasive media will have a axial force because of its property, because of the material we are using, and then the abrasion will take place. Yeah. So the major parameters in this particular process are extrusion pressure, number of cycles, flow volume and its speed. And coming to media related parameters, we have media viscosity, rheology, abrasive type, size and concentration. Workpiece configuration like restricting passage length and area, workpiece hardness, etc. Yeah. So coming to this particular process, the three major important elements in this particular process are the machine first. It has hydraulic pressure, it has the control of number of cycles, flow volume and flow rate, etc. And second important is the flexible abrasive media. So that is viscoelastic media we are using, and this viscoelastic media is used for finishing the complex geometries. For example, like you take a viscoelastic gel such as our toothpaste. So whenever you apply pressure, when you just take the toothpaste on the brush and add some salt particles and apply pressure and brush your teeth. So that viscoelastic gel will carry that salt particle, and then the result may be better shining of our teeth, right? It depends upon pressure. If you increase pressure, sometimes blood also will come, okay, based on the pressure, okay. And the polymer gel should have the properties, okay. It should carry that abrasives successfully, okay. When you put sand particles in the water, the sand will settle down. It cannot carry successfully. But when you put sand particles in a grease or oil, it will carry to some extent. It also depends upon the viscosity of the material we are using. So people have done two different major area of research in this particular abrasive flow machining. Okay, one is product development. The second one is process development. Product development, people worked on developing new media. Means some used polymer gel, some used wax material, okay, some used like different like rubber milk and different types of milks, different types of rubber, synthetic rubbers, etc. And they mixed with abrasives and they got patents in this particular field, and they tried different polymer gels for mixing the abrasive particles, and they compared with the existing abrasive media. So that is one area. Some used honeybee wax. Okay, they mixed honeybee wax with abrasive particles and then they tried finishing. So like that, one is product development. Next is process development. Process development, like they added some hybridization in the existing process. like by vibrating the workpiece, by vibrating the media, or by adding some magnetic field around the tooling, or by integrating a rotary workpiece in the field. So like that, people worked on process development. Okay. During my research work, I worked on product development. So we have developed one alternate media for finishing, and we patented it. And second is we worked on process development, like we rotated the workpiece while abrasive flow machining is on, and parallelly we vibrated the flexible tool while the abrasive flow machining is on. So that also we worked on the process development. So this is the setup, laboratory based setup developed in the NIT Varangal lab. So this is based on DST project equipment. So this is a 3D design and then fabrication. This is the tooling. You can see the two-way acting cylinders. Yeah. So what is our objective? So the objective is actually to finish some complex geometry, and we choose some small medical implant, okay, with some complex design, and we prepared a tooling for it. Tooling means fixture. So we prepared a fixture, and these small plates are used in a medical application. Okay, so that I will show. Yeah. So the second job is actually we prepared our own polymer gel and silicon carbide media. You can see the flexible tool how it looks like, and we fill the abrasive media in the machine. And we choose different abrasive particles in our case study, like different size, mesh size, and as well as the particle size. We varied. And preparation of workpiece, we choose laser cutting operation. Like we prepared several workpieces which are used as an implants, and these workpieces are made of SS316L. And we also use the another approach, that is additive manufacturing. So we prepared 3D printed titanium material. So we choose titanium and also stainless steel, which are orthopedic implants. And then you can see here the application is at ankle fracture. This T-shaped joints are used for additional support. So our target is actually to precisely finish this components. We cannot grind or we cannot use some simple process because of that complex shape. So you can see our students are working on the tooling and as well as the media, how it looks like while removing the fixture. So this is a fixture inside, like we have a primary tooling and secondary tooling. So inside we kept that orthopedic implant, and like after finishing you have to remove the media in this way. Like in the video also I have shown you, like they are working on different geometries. So the media is pliable in nature, so it will occupy the shape of the workpiece easily, and it will carry the abrasive particles also easily. Yeah. So like media before use and media after use, under microscope we observed, like before use how the abrasive particles are carrying successfully with the polymer gel, and after use, like the blunt abrasive particles were observed under microscope. So we conducted some experiments on surface finish, and we have recorded some RA values, so average roughness values. And when we observe at different cycles, you can see here at 50 cycles, the average roughness, and at 150 cycles. So what is cycle here? So when we pump the media from one cylinder to another cylinder, we count it as one cycle. So you like that when you perform for 150 cycles, 350 cycles and 450 cycles, we achieved the required finishing. We achieved the required finishing by increasing the number of cycles. And similarly, we measured the average roughness with respect to the number of cycles. And you can see at if the cycles number of cycles increases, the surface finish is increasing. Yeah. So you can see the NATW like this is initial during initial finishing stage. We and now right now we got some mirror image during the initial performance of that particular machine without proper optimization and without proper setting. We used to get a slight mirror image of that particular component. Yeah. So we understand the applications and all. Now I will tell you one limitation. So the limitation is low material removal rate, low finishing rate. Means it is taking number of cycles like 450 cycles for stainless steel. Just imagine for nickel based alloys how many cycles it takes, right? If the material is very hard, how many cycles it takes. So people worked on improving this finishing rate. So we also worked on improving its finishing rate, and many people worked on developing a hybrid method by combining two or more activities. We'll not go detail in all. We'll go where we worked and what is that case study and all. So simple abrasive prevention, you have some idea now. We pump the media from one cylinder to another cylinder, and hybrid AFM is the combination of two or more processes in order to get the additional advantage. Magnetic based abrasive flow machining. So there is one PhD on this. So the scholar from IIT Roorkee, he applied magnetic field around the tooling. And what happens if you apply magnetic field around the tooling? When he mixed the abrasive particles with iron carbon particles, and when the magnetic field is applied, he studied about the performance of media on magnetic materials and as well as non-magnetic materials. When the electromagnetic field is applied, the abrasive particles are mixed with iron carbon particles, and there is more interaction in the tooling in the work zone compared to simple AFM. So that's what they studied, and there are so many papers and the thesis on magnetic based AFM. And another scholar he worked on magneto-rheological abrasive flow machining. Means he studied the rheology of the media. So it means how the magnetic field and abrasive particles and iron carbon particles influencing while pumping the media to and fro. Okay, so like that, as I said, there is a process-based research where people worked on process, different means enhancing the process. So we worked on this particular area. So that is ultrasonic assisted abrasive flow machining and rotary based abrasive flow machining. Now our project is actually we combine these two, ultrasonic and rotary based abrasive flow machining. So first let us discuss what is this ultrasonic based abrasive flow machining. So we have a case study on this particular item, and then we will see the ML algorithms and their approach in this. Yeah. So here the setup looks horizontal. Whatever the setup right now we developed in NIT Warangal, it is vertical. This setup is developed in IIT Roorkee when I was working. So what is this setup? So this setup is a horizontal abrasive flow machining. So it is similar. It is similar to means it is similar means it is a simple horizontal AFM with additional attachment such as fixture, piezo actuator, and KCN15 amplifier and DC absorber. So we are using an actuator an actuator, piezo actuator, and we are vibrating the workpiece externally while pumping the abrasive laden media to and fro. So that additional vibration given to the workpiece externally will add some change in the mechanism. So what is that some change? That is explained here in the principles of material removal. So this is a cylindrical workpiece, and our target is actually to finish this internal geometry of the cylindrical workpiece. So when we pump the media to and fro, there are some abrasive particles which are active, and there are some abrasive particles which are inactive. Means if your workpiece is having more diameter, okay, larger diameter, there is a chance of abrasive particles simply rolling and sliding, okay, without targeting the surface. That kind of inactive particles are addressed by vibrating the workpiece. So what happens if you vibrate the workpiece at high frequency, like at 20 kilohertz frequency? When you vibrate at high frequency using a sinusoidal cycle, okay, at every time interval t1, t2, so there is a change in the amplitude of the workpiece, and due to that change, the abrasives inside the media are everywhere on the circumference of the cylindrical workpiece, and they are not moving straight, they are hitting at an angle theta when you vibrate at high frequency. So that's what we observed. So this is the simple simple workpiece with simple AFM process. And when you vibrate at high frequency, there is a scope of getting the inactive particle becoming active because of that high frequency vibration. So the result is we are trying to improve the finishing rate. So since the simple AFM takes hundreds of cycles, instead of that, if you make it hybrid, so we can finish it in less cycles, less number of cycles. So that's the idea. Yeah. So you can see that the abrasive hitting the asperity at t is equal to t1 when you are following sinusoidal cycle, and at different time intervals you can observe that the abrasive particle is actually participating the asperity hitting compared to simple AFM. So that is also observed under microscope and also atomic force microscopy, how the tiny chips are cut on a surface. Yeah, so let us take the case study. So first case study is based on that ultrasonic abrasive flow machining. Okay, now I hope you got some idea about what is abrasive flow machining and what is ultrasonic based abrasive flow machining. Because whenever you want to work with AI and ML, we should understand better the process first, because we are playing here with the parameters. We are playing with the parameters and their influence on the process. So before going to the case study, we have a strategy of experiment. So first, in the first phase, we should identify the known factors, unknown factors, and screen them. In the second phase, estimate effects and interaction and draw the curvature. And in the third factor, apply optimization using some response surface methods or any other optimization technique. Fourth phase, validation, and then confirmation and celebrate. Whatever the experiment we do, the strategy of experiment is important. Okay, so means before going to ML approach, we make sure that we have done the full factorial experiment or the design of experiment, and then generate the relation between the parameters and the responses, and you have some ANOVA analysis and then regression analysis, etc., before we apply any other algorithm, etc. We always take one small example in the classrooms also. Whenever you plan the strategy of the experiment, like how to make a cup of tea, so we have n number of trials. So the cup of tea, the combination of tea leaf, sugar, milk, and water will vary. If you ask some 10 students to prepare a cup of tea, there are known parameters, unknown parameters, interactive parameters, and result may be the taste of the tea and the color of the tea, right? So the final objective is how good you make the cup of tea, right? With the best optimization of the parameters. So the parameters will act as the known factors, the dependent factors, and the responses will act as the independent parameters. Means the taste of the tea will depend upon the quantity of milk and the water and the tea leaf you are adding, right? And the boiling time, etc. So like that, the strategy is important. So accordingly, we made a strategy for our workpiece preparation and then experimental setup. So these are the workpieces prepared. So one is targeted for internal finishing, and the other workpiece like the bevel care, it is targeted for external finishing using abrasive flow machining. And the media is prepared using 150 mesh, 200 mesh, 300 mesh, and 400 mesh. Means four different types of media are prepared with different mesh size, and you can see the flexible behavior of the media. So this is laboratory based developed media. And the chemical composition of the workpieces we have choose DNA steels and aluminum 202 series alloy. And the measurement and characterization formula used for the percentage improvement of surface finish, material removal, and we applied Taguchi analysis and also response surface methodology, etc. So percentage RA is higher the better. So we are converting that RA values in terms of percentage. Yeah. So coming to selected process parameters and their ranges. So it is very important to choose the levels and the ranges before we go to the main experiments. So while performing the experiment, we observed that the applied frequency or the ultrasonic frequency 0 to 20 kilohertz, and beyond that also you can go if your ultrasonic transducer permits that. And extrusion pressure we have up to 22 bar, abrasive mesh size 150 to 350, and processing time. So instead of number of cycles, we are counting the time. Okay, it means 4 minutes, 5 minutes, and up to 8 minutes, etc. And there are some parameters we made constant which are having less influence during the performance. Yeah. So some 31 experiments were conducted using response surface methodology while using ultrasonic assisted abrasive flow machining. So we have coded parameters like A, B, C, and D. Coded parameters means A is my applied frequency, B is extrusion pressure, C is mesh size, and D is the processing time. And we have recorded for the 31 experiments, we chose 5 levels, 4 parameters using response surface methodology. We conducted some 31 experiments and we have recorded delta. Delta means it's a percentage improvement of roughness, which is higher the better. And MR means the material removed. So the amount of the quantity of the material removed before finishing and after finishing, so we have recorded in milligrams. And based on the case study, we observed that the higher delta RA means the higher abrasive finishing we observed in the last experiment, that is the last run, when the applied frequency is 15 kilohertz and the extrusion pressure is 7 bar, and when we use 300 mesh size and the 7 minutes of processing time, we observed better delta RA, means better surface finish. However, the second output MR is not better, is not to the maximum best, okay, higher the best during that particular experiment. We observed the best MR during this particular run when where that A is 15, when the applied frequency is 15 and 7 bar of pressure and 200 mesh size and 7 minutes of time. It means that when you go for a multi-objective optimization, so we require higher the better for both the cases. So we need to work on the particular parameter and their ranges, which can give us higher the better in both the outputs. So we worked on that particular case, and also we varied some 5 levels and 4 parameters. Like for example, applied frequency is varied from 0 to 20. So we have a level, we have an experiment set on 0 and 5, 10, 15 and 20. But in between we don't have. In between we don't have a data set. And if you want to perform the experiment in between, so it takes a lot of time and also the material requirement, etc. Okay, the manufacturing will increase, the manufacturing cost will increase. So we thought of doing some prediction and confirmation experiment to identify the gap in the ranges given. And these are the regression models and regression equations generated for both outputs, that is surface finish improvement and material removal rate. And using these regression equations, we can identify the error percentage when we change the parameter values and how the responses are varying. So this graph shows the finishing through AFM and UAFM. AFM means abrasive flow machining. UAFM is ultrasonic assisted abrasive flow machining. We can observe the clear trend that whenever you are increasing the frequency, so there is an increase in the surface finish, and after some extent actually it is slowly deteriorating. That is maybe because of more abrasives interacting and forming some scratching because of high applied frequency. Similarly, we observe the trend when the applied frequency is increasing, so the material removal also increasing in the while doing the experiment. It confirms that the applied frequency is influencing a lot and it is playing a major role during the experimentation. When we observe the individual trend, like applied frequency, extrusion pressure, abrasive size, and processing time on the response 1, that is delta RA, we observe that there is an increasing trend in applied frequency, extrusion pressure, and whereas decreasing trend and then further increasing in abrasive size and processing time, there is an increasing trend, etc. We have presented combined effect of the parameters like extrusion pressure, processing time on delta RA, and also the combined effect and individual effect on MR as well. Okay, so coming to proof, so under microscope we observe that when the media is flowing on a cylindrical surface, the media is flowing means it is not flowing in a straight, it is moving at an angle theta, and that media flow direction has been changed when you vibrate the workpiece at high frequency, and the abrasive particle impact and the deep scratch formation is observed during the ultrasonic assisted abrasive flow machining. So the same images were taken at a different frequency, like at 5 kHz, 10 kHz, 15 and 20, to observe the penetration of abrasive particles on the targeted surface. So we have done ANOVA analysis, and coming to one particular approach, like we used fuzzy logic approach for prediction and also to prepare a model for that particular experiment to avoid that repetition of the experiments. So like as of now you got some idea, like we have done some experiments, some 31 experiments, real-time data has been collected, and then we use some parameters, some ranges, right? So based on the initial experimentation, and we have done thorough experimentation and generated regression analysis, a relation of the parameters with the responses and all that is everything done. But To avoid the repeatability and to predict the data properly, we use some easily available technique called fuzzy logic. So what is this fuzzy logic and how it helped in my particular manufacturing application? Fuzzy logic is an approach to variable processing that allows for multiple possible truth values to be processed through the same variable. Okay, washing machine. So we'll discuss the fuzzy logic checks for the extent of dirt and grease, the amount of soap and water to add, direction of spin, and so on. The machine rebalances washing load to ensure correct spinning. Else it reduces spinning speed if an imbalance is detected. Even distribution of washing load reduces spinning noise. I think we might have observed in our house, the machines will take the decision automatically. So it follows fuzzy logic, like based on the input you are giving. Based on the input you are giving, like the extent of dirt, grease, and the amount of water, soap, etc. Based on the input you are giving, accordingly, the machines will take decision on the outputs like the RPM and the other factors, etc. So, what is the difference between fuzzy logic and Boolean logic? So, in Boolean logic, like if the question is it cold? So, it will print either yes or no. Do you have fever means if yes, no means no. Okay. Whereas in fuzzy logic, it is a method that resembles human reasoning. Okay? This approach is similar to human perform decision making. So it will print all the data in between that yes and no, or 0 or 1. Is it cold means very much cold, little cold, very less cold, etc. So we will see in our case study how we implemented that fuzzy logic and how it helped in prediction. So the main elements of this fuzzy logic system are rule-based, fuzzifier, interference engine, and defuzzifier. So input and output loop. So fuzzy logic architecture looks like this. So we use the rule-based method, and how the rules are framed, etc. we'll discuss. Rule-based, so it contains the set of rules and if then conditions provided by the experts to govern the decision making system on the basis of linguistic information. Recent developments in fuzzy theory offer several effective methods for the design and tuning of fuzzy controllers. So we can understand the elements of the fuzzy logic engine, like fuzzy logic classification system, what is the function of fuzzification, interference, and defuzzification, etc. Coming to rule base, like we'll discuss on how the rules are framed, etc. for this particular study. So we have developed a input and output parameters and their ranges in a fuzzy system. So input and output parameters like A, B, C, D. A is nothing but my applied frequency, B is my extrusion pressure, C is processing time, sorry, C is the abrasive size, and D is the processing time. So we developed a membership functions for all the 4 parameters, and we have given the ranges called low, medium, and high. So it will print from 0 to 1. In between, whatever the result, like low, medium, and high ranges were given. And similarly, the simulation blocks of the fuzzy logic model are constructed using the MATLAB, and we also created a membership functions for the output responses. So my output response is surface finish improvement and material removal. So I have given the ranges for low, medium, and high for the surface finish improvement and as well as material removal. So these ranges I got from the real time data, okay, based on my 31 experiments, whatever I have conducted. Based on that, I have given ranges for low, medium, and high. Now, how to activate this fuzzy logic controller? So we need to give the rule-based interface. So, like how the rules are framed, if and then rules. If you go back to our experimental data, yeah. If you go back to this experimental data, like the rules are framed in such a way that if A is 15, means if A is 15, 15 comes under the high range. If A is high and B is high because 17 is high and C is high because 300 is high in my case and D is medium, okay, then the the delta RA, the percentage RA comes under the medium range because my higher range is 80 and lower range is something around 35 to 40. So it comes under the medium and my MR is under the medium again. So that is that like in that way, different permutations and combinations we have written the rules. Like another example, if A is low, B is low, C is low, and D is high, then my delta RA will be low and MR will be high. So according to this particular result. Take the another condition like when ultrasonic frequency is 0. Okay, if A is 0, means if my ultrasonic frequency is 0 and my extrusion pressure is medium and C is in the medium and D is medium, then my result is also coming in the medium range and as well as MR is in the higher range because my highest value achieved is 14. So like that number of rules were given as an input to the fuzzy rule based interface engine and it started giving response. Like for example, if I give my A as 3.
I just want to know how did you define your low, medium, high threshold?
Yeah, so these are defined based on my experimental data. So based on that experimental data only we have defined. Yeah. So this particular experiment we can see here means this prediction. We have used 3 ultrasonic frequency and 5 extrusion pressure and 800 mesh and 3 minutes of processing data. So it started giving result like the surface finish could be approximately 34% and MR would be approximately 10%. Okay, and similarly when we conducted some more prediction like when A is 17, which is not done in the experimentation, and B is 19, you might have seen in the video like if you want to repeat the experimentation, you have to prepare the media and you have to ensure that abrasives are not blunt and you have to ensure several things to perform the experimentation. Here we are getting the data without experimentation, but however we have conducted again a confirmation experiments like we have conducted some 5 experiments where the data is not available in the main data set. So if A is 3, B is 5, C is 800 mesh size and D is 3 minutes of processing time. We have calculated experimentally how much we are getting and using regression analysis how much we are getting and using fuzzy logic how much we are getting and parallelly we have identified the error percentage. So the error percentage of regression, error percentage of fuzzy and error percentage of for 2 outputs. So that is surface finish and MR. So somewhere we found fuzzy is giving more error, but it is not it is not it is not observed in the other confirmation experiments. So the fuzzy logic started predicting based on the knowledge given to it using the fuzzy rules. And you can see that experimental fuzzy and regression analysis how closely interacting based on when on the x-axis if you are varying the ultrasonic frequency, on the y-axis surface finish improvement and the material removal, etc. Yeah. So when you observe the case study, we vibrated the workpiece in a radial direction, means perpendicular to the media flow direction. In another case study, we vibrated the workpiece in axial direction. axial direction, and then we have conducted the experiments again. And the novelty comes when you vibrate axially, what is the surface response and what are the parameters that are acting and how the surface finish improves, MR improves, etc. while performing in an axial direction. So that case study also we have done, and we have performed a similar kind of exercise. I'm not going into detail about that, but I wanted to tell you that, okay, like we can perform different set of experiments, different data can be generated by vibrating, by changing the vibration direction, etc. to understand the performance. So I will skip this. When we vibrate the axial direction, I'm skipping this. Yeah. So coming to Jaya algorithm. Have anyone worked on Jaya algorithm or Rao's algorithm, etc.? So this is one of the popular algorithm. Like, anyone worked on TLBO, teaching learning based algorithms? Yeah. So there is one professor R.V. Rao from NIT Surat. Someone might be knowing. So he started introducing these algorithms. These are majorly optimization algorithms. Okay, supervised learning. These algorithm have some beauty. Okay, this will give you the best solution always. Okay, so we applied this algorithm, and I will show you some results also. So this J algorithm is first introduced by Professor R.V. Rao in 2011. So the flow chart of the algorithm is like start, define population size, number of variables, and termination principle. Best solution, worst solution, you need to define carefully, and then there is a coding here. There is a coding, and then further coding to decode it actually. So we have another slide here. First, we need to define population size, number of variables, and we need to define the number of variables and termination principle. F of x. F of x is the objective function here. Like after performing that response surface methodology, we got the objective functions like regression equation for surface finish and as well as MR, right? So that is our objective function F of x. And we should define here the best solution and worst solution. What is best solution in my case? Higher MR is the best solution. Higher surface finish or better surface finish is the best solution. Worst solution is low MRR, means low finishing rate, and low surface finish, or the worst solution. So I need to define here the best solution and worst solution. And in the coding, what happens is the new parameter value is printed based on the old value plus random number, like bracket best solution minus old minus random number into worst solution minus old. Okay, so here based on this logic, what happens means the best solution is always taken forward, and the worst solution is always neglected. So just I will like to show the Excel. So lose connection. HTML1. That's complete. Yeah. So if you observe, like the J algorithm codes are given, we have given input parameters A, B, C, D, and the objective function f of x regression equation using the J algorithm code, and our initial population size and number of parameters are defined, ranges are defined. Randomly, the A, B, C, D are generated. A, B, C are nothing but my parameters, and f of x is my objective function. So what happens is, for every iteration, it will print the best value and the worst value. So we have defined in the coding what is best and what is worst, right? Accordingly, for every iteration, it will generate the best value and worst value. And then in the next second iteration step, it will compare the worst value of the previous first generation, and then it takes the best among the worst and then move on. So like that, slowly it will print the best value, worst value, and then it will come to a conclusion of giving the optimum results. Optimum results finally, like the best solution is this, and you use these parameters like 20 kilohertz frequency, 20 kilohertz frequency, and 350 abrasive size, and say 2 minutes of processing time, you will be getting the best solution. So like that, okay, best solution. So similarly for MR, you see. So for MR, so MR, let us say higher is the best solution and lower is the worst solution. Okay, so here A, B, C, D are my parameters. All random values are generated in between the ranges. For example, if I give a range of 0 to 20, it will generate a random value from 0 to 20. And similarly, B is my extrusion pressure, and C is my abrasive size, and D is my processing time. It will generate a random value, okay, in between the ranges, and f of x is my objective function, which is defined. And we also define what is the best solution, what is the worst solution. Best solution is MR, higher the better is my best solution. Okay, and worst solution is lower the better. So it will continue the number of generations by replacing the best solution and the worst solution, and it will take the best among the worst and move forward. So it will give you the best solution at 19.11 bar. When you use 20 kilohertz frequency, 2 bar pressure, 150 mesh size, and 8 minutes of processing time, the data is showing best solution for individual output, right? For the single output. When we combine both, okay, so when we combine both also, we have studied like how the parameters are varying and how the response is coming. In my case, I required surface finish higher the better, MR higher the better. So I combined both the equations and given input in the coding, and when we run it, so it will give you some best solution when you use this particular components. When you use 20 kilohertz frequency, 350 mesh size, and 8 minutes processing time, and 2 bar of pressure. Okay, so like that, we have studied few results, and we have published based on that algorithm, based on J algorithm. And what is the motivation to perform this is, I will show you some papers. So ML based papers. So nano finishing Jaya paper, like we are discussing on some finishing techniques and using J algorithm, how it can be approached. Okay, a new optimization algorithm for parametric optimization of nano finishing methods. So here in this paper, you can see, you can directly take the regression equations from the already published papers, like by giving the suitable reference. Like they referred this particular paper, they referred my data and they have done that best solution and worst solution as well. So here you can see that J algorithm is defined. So the coded value and then how we proceed, how we accept and replace the previous solution and keep the previous solution and proceed. Here I wanted to show that they worked on optimization of parameters on abrasive flow machining, whatever we are discussing now. And you can see the parameter ranges and the constraints and the MR equation, regression equation and RA equation and the ranges, the 4 parameters ranges and all. Rotary abrasive flow machining and their parameters, ranges and the convergence graphs. Finally, this is the result they are printing, like the best solution and the worst solution and the computational time recorded for the parameters. And then they have compared these studies with already proven technique like genetic algorithm and all. And similarly, they worked. Okay, so these codes are available. These codes are available on internet also. Like while we are first time doing, so we have seen one paper and then we used MATLAB and then we used our own f of x objective function and then we have given the ranges for our parameters and then we run the code and we got some results like convergence graphs and then results and then published. Okay, so you can see that applications in thermal applications, J algorithm in thermal applications, multi-objective optimization algorithm. And coming to fuzzy and ANFIS model, so we have some papers with the CNC milling data publishing using ANFIS model. And we also published that fuzzy based technique in abrasive flow machining model. So these are some of the results we can see, like where the mechanical engineer can collaborate with computer science engineer and develop some models based on the realistic data, how we generate the models and then start predicting. So like that we are working using different algorithms. Recently one of my student, he also worked on different machine learning algorithms. I will show you that data. So these are some of the data we worked. Now our students also showing interest in working this. So it's not working. Yeah. So before giving a small break, actually, I would like to show one of the advanced finishing method we developed, and then we are working on AIML applications as well. So this small technique you can also develop in your labs. And now one PhD scholar finished working on this, and another PhD scholar recently joined working on this particular application. So there is some issue with the laptop. So you can see here we have developed a magnetic abrasive finishing process and using a simple vertical milling machine. And we introduced ultrasonic vibrations to the workpiece. And we simply developed a tool using the winding, and then we made electromagnet. So you can see how the system has been made. simple vertical milling machine. We developed a small tool, electromagnetic tool, and there is a gap between the workpiece and tool. In between, the abrasives are mixed with magnetic particles. You can see that magnetic abrasive brush is formed. So that flexible brush is formed, and that flexible brush will remove the material. So once that electromagnetic field is applied, the flexible magnetic abrasive brush will remove the asperities and start finishing. You can see that grinding marks in the pit holes before and after finishing. Yeah. So before going to a small break and the article discussion, so I would like to just conclude based on whatever we have discussed. So this is ultrasonic assisted UMF. Yeah. Yeah. So based on our discussion, so we discussed about simple abrasive flow machining and its working, and ultrasonic assisted abrasive flow machining and its working, and how the experimentation has been done, parameter level setting, and then responses, how we recorded, and how the regression analysis has been done, and the fuzzy logic, etc. Fuzzy logic, how we applied and how it helped in prediction, and J algorithm, of course, to perform the multi-objective optimization and all. And we have developed another setup called magnetic abrasive finishing, and we work the same thing, like developing the data, generating the data, and then integrating the machine learning algorithms for that particular data. And small work I would like to show here in the recent PG students. So they worked on random forest method, XGBoost, and ANN method. They trained the data that they got the experimental data using the existing setup. So this is particularly this data particularly we worked on a implant finishing. So this we already submitted in a paper, Q1 paper. So there are parameters like extrusion pressure, number of cycle, abrasive grid size, initial and RA and final RA, etc. And the percentage delta RA is recorded. So we are working on like ML model validation and integration for different methods, like you can see here. We are comparing them, and then this is the architecture of the ANN we have developed. And then we are working on like what is the like different methods and their approaches, comparing with the experimental data. So this work is not yet finished. So we are working on generating different algorithms, that particular data on the orthopedic implant. So one paper which was submitted is based on the experimental findings of orthopedic implant, and the second paper we are working on ML approach in finishing that orthopedic implant. So that is what we are currently working on. Yeah. So these are some of the advanced finishing methods we are working, and due to lack of time, I cannot go in detail about magnetic abrasive finishing and other things. So before going to break, we can have some small question and answers, and then we'll discuss that simulation of media behavior paper, and then yeah. So that's the plan. Any questions quickly, please?
Have you used SVM?
No.
Robot vector.
No.
Right now, that is the very
Yeah. So
you can have used it. Be quite convenient for.
sure. We have so far not used.
Because fuzzy logic plus SVM
Will give you better. Yes. That's a good suggestion. If the data sets are there, we can collaborate and work also. Yeah.
The thing is, you have to train the model.
Yes. We can collaborate and work also if you require. Okay.
You are more expert in that.
Yeah. So any other things? Or we can just take some small break and then we'll discuss that article. Okay, so like so far I have not discussed the simulation aspects. So the paper we choose is the simulation based. Continue. Yeah.
Have used this gray regression analysis, the JR,
Yeah. Yeah.
and JR algorithm
J-
is almost similar to that.
Yes.
But in GRA, we were actually normalizing the data. I never saw any normalization process in JR algorithm. It is like all raw data has been considered.
Yeah.
Is it so, sir, or is there any normalization process?
Means we use the objective functions, the regression analysis data, and then only beauty in this is actually we are minimizing that worst solution and trying to get that best solution. So more or less,
The
Yeah.
same data we are
Yeah.
we are not normalizing.
we are not normalizing.
And we can have multiple objectives.
Yeah.
Also. Higher
Yes.
the better,
Yes.
lower the better.
Yes.
Together we can analyze.
Multiple objective we can do when you involve both the regression equations in a single
Okay.
effort.
That's what in
Yeah.
ray regression we actually find the GRG value.
Hmm.
So that is where while finding the GRG value only we're going to convert the data, normalize the data according to their objectives. Whether it is higher the better or lower the better, we'll analyze there only, and then we'll derive one single value in GRG. But here I didn't see any process like
Yeah.
that. So
It is slightly different. You
But
can
it's
try,
similar to
yeah, similar, but the thing is you will get best solution compared to that, because that equation, that coding is given in such a way,
nice.
so it will filter like anything.
So we can run these codes in
Yeah, in MATLAB.
Thank you.
Yes. Yeah, so we will continue with the article discussion as well. It is not going full screen. Shall I restart?
No problem, sir. I think the PPT is open here. This is
Let's see, you close it. Okay, no problem.
where is the PPT, sir?
Full screen.
It is posted. So
Yeah. So in the article discussion, I hope you have gone through the paper, okay, because it is also already published in the brochure as well. Otherwise, you please go through today. So this is an interesting article, like simulation of media behavior in vibration assisted abrasive commissioning, and it is published in Q1 Simulation Media Practice Journal elsewhere. So this particular article deals with several simulation aspects when we are working on vibration assisted abrasive flow machine. Yeah, so there is a small video. Yeah, so when we developed the setup, initially we made a 3D setup. So here you can see that fixture and the workpiece we are vibrating at high frequency and then pumping the media to and fro. So this is developed in a SolidWorks, and then this same design entirely we fabricated for a real-time machining purpose. So here we studied the simulation of the media behavior inside the workpiece when it is vibrating at high frequency. So the article talks about that. In a simple AFM, what is the media behavior inside, and when we vibrate at high frequency, so what is the media behavior inside? Like when you vibrate at high frequency, what happens to the abrasive particles hitting on the target surface, and what is the temperature distribution, velocity distribution, and wall shear distribution during the simulation. Okay. Yeah. So here you can see the 3D mesh model of the fixture, and we have taken only the flow of the abrasive media inside the fixture. So this is our inlet and this is our outlet, and we can see the finer mesh of the workpiece, and it is dynamic workpiece because we are vibrating at high frequency, and this is the media flow region inside the fixture. And I will show you some improvements also what we are working in 2025 as well. So these are the boundary conditions and the parameters used in classical AFM and ultrasonic assisted AFM. And grid independency test is performed to find out the number of elements at what particular stage we are getting converged, and the number of nodes, elements, mesh type, element size, number of iterations were recorded in the paper. Like you can see, this is the workpiece where we have used coarse mesh and the finer mesh. Yeah. So coming to simulation, like you can see here, we have performed the simulation when we are vibrating the workpiece at higher frequency, how the media flow behavior inside the workpiece. So we have generated result for pressure distribution in the simple AFM process, in the UAFM process with 10 micron amplitude and with 50 micron amplitude. So what is the difference in the pressure distribution inside the workpiece? So this is the workpiece from starting inlet to outlet. And we observe that there is a slight increase, decrease in the pressure distribution, whereas increase in the velocity. So these are the contours of the pressure distribution inside the workpiece when you are vibrating the media inside the workpiece. And these are the velocity distribution of simple AFM black in color and UAFM in blue color, and UAFM at a different micron amplitude in a red color. You can see that velocity distribution, how it is varying when you are vibrating the workpiece. So these kind of studies we have made, like you can see the simulation resultant velocity contour when inside the workpiece. Inside the workpiece, how the media simulation resultant velocity will works. And when we compare, when we correlate with the experimental, we observed that velocity vector distribution in the simple AFM and UAFM process. And it is observed that in the simple AFM, the abrasive particles are hitting the target in a straight line, whereas when you are vibrating the workpiece at higher frequency, the abrasive particles are hitting at an angle theta, and we try to prove using the SEM analysis. When we vibrate the frequency, we observe that deep abrasive scratches at an angle theta. And temperature distribution of the media we observed, like under simple AFM and under UAFM, what is the difference? So when you vibrate the workpiece at higher frequency, it is expected that the abrasives will have more interaction with the asperities, and the temperature may rise during the abrasive flow machining. That's why we simulated the temperature distribution, and it is observed that the change in the temperature range, the rise, will not affect the machining parameters and the work surface. And temperature distribution contour you can see, and this contour is correlated with the thermogrametric analysis to see the reaction, the time versus temperature, endothermic and exothermic reaction when the media is flowing inside the workpiece when it is vibrated at high frequency. And we have done simulation on the external surfaces such as bevel gear. So the bevel gear is taken as the workpiece, and you can see the mesh model of the bevel gear and the fixture of the bevel gear. And these are the process parameters and simulation settings. And you can see the media flow on a bevel gear. Its velocity distribution, pressure distribution, and temperature distribution, etc., were recorded. And it also observed the, the penetration of abrasive particle hitting at an angle theta. And we observed under microscope how the boring marks and the grinding marks finished by using ultrasonic assisted abrasive flow machining under scanning electron microscopy. These are acting as a support for the simulation result, and these are experimentally fabricated setup and the fixture for the bevel gear. This we have published in Machine Tools and Manufacture Journal, one of the prestigious journal. So the journal talks about finishing of a bevel gear using ultrasonic assisted abrasive flow machining. So this is published in Machine Tools and Manufacture Journal. So this talks mainly on the abrasive particles and its penetration and its oscillations and its effect on finishing, finishing a bevel gear. So we have discussed one important parameter. As I said, by giving ultrasonic vibrations, it will minimize the processing time, means it will improve the finishing rate, right? So it will improve the rapid of the, means the process will become rapid, like by introducing the vibrations. So we have done a small case study, like we have done some experiments using frequency as 19 kilohertz, 10 amplitude and 30 extrusion pressure, 5, 10, 15 as a processing time by varying the processing time, and the remaining parameters all constant. We have conducted a small case study on UAFM, frequency and amplitude, and AFM with zero frequency and zero amplitude, simple AFM. So the result shows an interesting observation, that is, on a y-axis you can see surface finish improvement and the x-axis processing time. So when the processing time is increasing, it is following increasing trend in both cases, whereas with 5 minutes of processing time in simple AFM, we could achieve only 35% improvement, and with 15 minutes of processing time, we could achieve only 55% of improvement, whereas with 5 minutes of processing time with ultrasonic frequency, we could achieve 65%, nearly 65% improvement, which you could not achieve even after 15 minutes of processing time using simple AFM process. So this is the same result is observed in material removal, and we concluded that the process has become rapid and fast when we vibrate at higher frequency. And we recorded morphology of the machine surface under optical microscope and also under some analysis, how the deep feed marks of the bevel gear and the rough surface are performed smoother using ultrasonic assisted abrasive flow machining. So right now we are working on simulation of media behavior on orthopedic implant using abrasive flow machining and hybrid AFM. So here I will show you, like so this is a fixture developed, and this is a workpiece, a mesh model of the workpiece, and you can see the simulation for velocity streamlines inside the fixture. And we have recorded the 3 different mesh and 3 different levels of the mesh size of the workpiece, and these are the parameters, and these are some of the results on a implant, how the velocity contours are distributed and how the streamlines with vibration, without vibration, and how the pressure distribution on an implant, wall shear stress contour, and volume fraction contour, strain rate, velocity profile distribution. And we are working on pressure drop analysis, why the pressure, what is the reason for that analysis. And quickly I'll show this, sir. So theoretically also we have compared with the numerical data and as well as experimental data, and we followed the pressure distribution analysis. For a cylindrical workpiece also, now we have vibrated the workpiece, we have rotated the workpiece, and when we combine the vibration and rotation, how the media simulation is happening inside the workpiece. So we are working on all these advancements. When I compare with the paper already published on simulation of media behavior with ultrasonic abrasive flow machining, now we are comparing when we rotate the workpiece, what will be the abrasive flow media behavior, and when we vibrate, what will be the abrasive flow behavior on a implant, and when we combine both also, what will happen. And similarly, we are trying to trying to do some experiments. We have developed a setup as well and compare the experiments with the numerical data, theoretical data, and the simulation data. Yeah, so you just can you go through the paper and then come back to me if any discussions are there. Yeah, so now the session is open for the question and answers before we close for the today's session. Yeah.
Regarding the amplitude of vibration, is there any influence in terms of?
Yeah, there is very less influence. So we tried 10 microns and 50 microns. Hardly we find the influence. Whereas when we are working experimentally, we choose a constant amplitude because of the constraint of the equipment. So that's what I observed. Yes, both. We tried both, sir. Radial and as well as axial. So now we are working on an implant, how the media behavior on an implant, and also we are working on rotary plus ultrasound. If combinedly both, so that's what we are at present we are working on that particular project. Yes. So any other questions? You can email me if any particular questions because of the time constraint. So you can discuss later also. You can email me. And if anyone is interested in this particular area, we have a setup at NIT Warangal. So we can work together if like ML based or some simulation data. So we are open for the collaboration. If no doubts are there, I will close the session. Thank you.
Thank you, sir. The lunch is arranged in the boys' hostel. So please join us for the lunch, and next session starts around 2:15, the same place. And I would request Professor to share the material